Yes, so today we have Miranda talking to us about ideal pseudorandom codes with applications to watermarking generative AI.
So first I'll say that I'm going to try to cover two papers in this talk. The first is pseudorandom error correcting codes with Sam Gunn. The second is ideal pseudorandom codes with Omar Al-Rabia, Prabhanshan Anand, Yevgeny Dodas, and also Sam Gunn. Okay. So what I'm going to try to fit into this talk is first just a little bit of background about watermarking, and then I will tell you how pseudorandom codes solve the problem of watermarking generative AI, and also why they're necessary for watermarking generative AI. And then I'll tell you more about my new paper. The first part of that will be on what are called adaptively robust pseudorandom codes, and then I'll talk a little bit about ideal pseudorandom. And if you take away one thing from this talk, it's that pseudorandom codes are a brand new cryptographic primitive, which I hope are useful for more than just watermarking. But at the very least, they're very useful for watermarking AI-generated content. Okay, so the problem I'll start with is, say you have some text, all you have is the text, and you want to know whether it was generated by a human or by some AI. And here, this is like some bad cryptography. And a natural approach to solving this problem is just to train a classifier to distinguish between AI-generated text and natural text. And people have actually done this. There are services online where you can use these tools, but unfortunately, they have some problems. And one of them is that they're very easy to avoid. So for most models, if you just like prompt it and then ask very nicely to evade detection, it's actually pretty good at evading these detectors. And then on the other hand, there's a high rate of false positives. For example, this is the US Constitution, and one of these tools is very confident that it was AI generated. And this is like kind of funny, but these false positives actually have caused some real problems. For example, students have failed due to false accusations. And these false positives are more likely among non-native English writers, which is pretty problematic. And so for these reasons, organizations have been moving away from using these post-hoc detectors. So what I'll be talking about instead is watermarks. And watermarks are a way to more reliably distinguish AI-generated content. And there's been a lot of exciting work on language model watermarks specifically. And lots of work from the cryptography community, which is sort of how I found this problem. And these works nicely achieve provable guarantees. For example, you can actually prove that these watermarks are robust to attackers that take the watermark content and make certain classes of transformations. These watermarks also have a provably negligible false positive rate, so you can make sure that there are none of these false accusations. And finally, some of these watermarks even preserve the quality of the content that's being watermarked. Okay, but so far, until pseudorandom codes, there was no scheme that was simultaneously quality preserving and robust. So all of the schemes listed sort of traded off between quality and robustness, but couldn't achieve both simultaneously. And when I say quality preserving, I mean something very strong, which is that you shouldn't be able to distinguish between watermarked content and content generated by the original model. So in particular, like the watermark shouldn't be introducing any observable quality degradation, where observable is to like a polynomial time algorithm. Okay. And by the way, feel free to stop me with questions at any time. Okay, so first I'll sort of cover the watermarking approach that was introduced in pseudorandom codes. And here, when I talk about a watermark, what I mean is some sort of wrapper around a model M that allows the user to query with a prompt and then obtain some watermarked content. So here, like the access to the watermarked model should look basically the same as the access you had to the original model. The only difference is that the content should be watermarked. And a watermark also comes with a detection algorithm. So someone can query some content and then get back an answer of whether or not it's watermarked. And here, the watermark algorithm and also the detection algorithm make use of a shared secret key. So I'll basically only be talking about secret key watermarks today. Okay.
What was M there?
Oh, M is some model. So the watermarking scheme takes some already trained model and it just uses query access to that to introduce the watermark.
So to detect you need the secret key. Does that mean that like third parties can no longer detect, right? So OpenAI, I'd have to ask OpenAI if this was generated by ChatGPT.
Yeah.
Okay.
Okay. And so the watermarking scheme that I'll introduce is very general. It applies to any generative algorithm that has sufficient randomness in the content that it generates. So what I mean by this is I'll consider generative algorithms that take some input, and along with the input, they also take a fairly long random string. They use the input and the randomness to together produce some content. And in addition to this, I'll also require that the algorithm has some approximate randomness recovery procedure that takes the content and outputs an approximation of the randomness that was used to generate it. And I'll ask you to just believe that these randomness recovery algorithms exist for real-world generative models. It turns out that they exist for image models, and we actually prove in the paper that they exist for LLMs. Yeah, so it's maybe a bit surprising, but it's true, and these things are really practical and quite simple. Okay. And just to give like something concrete to this framework, you can imagine that we might have an image model and you prompt it with something like you're asking for a cat image. Then usually these image models work by first generating some random latent features, and then they map the latent features to a content, in our case, a cat image. And it turns out that there's a way to go from this content back to the randomness using an algorithm called an encoder. And these exist. Okay, and so in order to do our watermark, we're going to focus on the randomness in this procedure. Specifically, we're going to focus on like this procedure where the randomness goes through the algorithm to the content. And then once we have the content, we can reverse to get back an approximation of the original randomness. And our observation in pseudorandom codes is that you can actually think of this whole process as a noisy channel that's acting on the randomness. So just like redrawing what I had before, you have your randomness, you use it to generate your content, and then you do randomness recovery. And what you get back is a corrupted version of the randomness that you started with. And it turns out that for like real generative models, what you recover is in fact a noisy version of the randomness you started with. In particular, typically the error rate is constant. So you can imagine that if the randomness you started is binary, which is the setting I'll consider in this talk, then what you get back has a rate of errors that's maybe like 40% of the bits are flipped. So it's constant, but it's a fairly high constant. Okay. And now our watermark is quite simple. What we do is we just replace the randomness with a pseudorandom code word. I'll tell you formally what those are in a minute. Now to detect the watermark, if we're given some content, we just use approximate randomness recovery to get back this R prime. And then we check whether R prime is close to a code word using our secret key. And this whole functionality will be handled by the pseudorandom code. Okay, so it's very important here that the code word is pseudorandom because this is what gets us quality. In particular, you can't efficiently distinguish between the original process of generating content and this new watermark process because we're just replacing uniform randomness with pseudorandomness.
So you define the approximate randomness recovery for inputs which were generated by the LLM. So what if like you give a human generated text, you need some sort of guarantee, right, that this error black box will not just spit out something that, something good for human generated text.
Yeah, that's a really good point. So what we actually proved is that the amount of error introduced by randomness recovery for LLMs depends on the amount of entropy in the generated text. So if you ask the model to output some fixed text, then there would be 0 entropy here. And so the error rate would be like 100%.
I think Sagney's question was different, which was like, okay, say you're trying to test, and correct me if I'm wrong, so you're trying to test a given piece of text was generated by a human, then you have to run randomness recovery on this piece of text, and like, wait, that's not even defined yet.
Yes.
I think the idea, well, I'll let you answer.
Yeah, so if you run randomness recovery on a human generated text, then you get some binary string. And now with overwhelming probability, this will be far from all code words.
Okay.
Yeah, it would just have to be like really decorrelated. Like something that
So there's an extra assumption on the approximate randomness recovery process.
Well, there's no assumption. A property of the pseudorandom code is for any fixed string, only with negligible probability over the key is it close to any code word.
And then like the randomness recovery procedure is decorrelated with the setup randomness pseudorandom code words. So even when you randomness recovery, it doesn't take it.
That was the same. So
yeah.
Copy of
Yeah, so importantly also randomness recovery does not depend on the secret key.
Okay.
Okay, any questions before I define pseudorandom codes? Okay. Oh, I guess I should say the reason why we need it to be a code word rather than just any pseudorandom string is it needs to withstand the noise added by this whole process. Okay, so I want you to think of a pseudorandom code as simply a pseudorandom encryption scheme where decryption can tolerate a high rate of errors. More specifically, a pseudorandom code satisfies pseudorandomness and error correction, where pseudorandomness is CPA-style pseudorandomness. So in particular, a distinguisher can query any messages of its choice, even the same message over and over again, and the ciphertext it gets back should look independently random. Error correction says that if you take any ciphertext or code word and you add low weight error to it, then the probability that the decoder recovers a different message is negligible.
But this error correction definition could capture attack like water.
That's right. So, okay. For now, we're only going to consider binary code words and random bit flips. In the papers, we do have robustness to other error channels, maybe channels that delete bits instead, not reordering though. Yeah, like deletions and insertions. But for now, you can think of the errors as just bit flips.
That notion has been considered in the literature.
Yeah. Okay, and also everything I'll talk about today is secret key PRCs, but we also have public key PRCs, which are analogous to public key encryption. So the main result from CG24 pseudorandom codes is that we actually construct these pseudorandom codes assuming subexponential hardness of LPN. And while I've only talked about the property that you can efficiently check if something is close to a code word, in the paper, we actually have pseudorandom codes that can encode longer messages, and they even have linear rate. And they're robust to any constant rate of random bit flips and random deletions. Yeah, so I'll show the construction later, but I'm just stating this for now. And I guess I'll point out that if the PRC has error tolerance that's greater than the amount of error introduced by just this randomness recovery algorithm, then this extra error tolerance translates to robustness of the watermark. So you can imagine like an adversary takes some content and then adds more modifications. Maybe in the case of text, they change some words. This usually just translates to more errors on the recovered R prime, which hopefully the PRC can handle. So not only is the PRC like what you need for instantiating this template, the error correction also gets you this extra property of robustness, kind of for free. Okay, and so instantiating this template with a pseudo-random code, we constructed the first entirely quality preserving or undetectable LLM watermark with robustness to any constant rate of random word substitutions and random word deletions.
Isn't it like little O1 deletions or something in the original paper? Or am I wrong? It's O1.
Yeah. Okay. Yeah, and in fact, it can be any constant. I guess, yeah. And just to highlight some other works on pseudorandom code since the first paper.
So it's deletion, it's not worst case deletion, so it's like average case, right?
Yeah, so it's a little bit stronger than average case, but the definition is a bit subtle and weird. In this talk, I'll talk about a much stronger version of robustness than we have. Okay, so my co-author Sam, along with Xuandong Zhao and Don Song from Berkeley, actually use pseudorandom codes to watermark images in like a very practical way. So this is an iClear paper, and they run the standard benchmarks on this watermark, and it, I think, is state of the art. So this is not just a theoretical object, it's really practical. There's also been this work appearing at Oakland where they construct what are called multi-user watermarks, and they also study a stronger adaptive robustness property of watermarks that you might want. I'll talk more about this property later.
Do they have an implementation? Last time I checked, there was no.
I don't think so.
Yeah, it's like the only Oakland paper I've ever seen without an implementation. Yeah,
Yeah, it's a cool paper. I was a bit surprised that it went to Oakland because it's more theoretical.
Yeah.
There's also this work of Golowich and Moitra, where they construct pseudorandom codes that are robust to edits, so insertions and deletions, rather than just like binary bit flips. And then Gentiala and Guruswamy construct pseudorandom codes from different assumptions, rather than just subexponential LPN, and also consider weaker kinds of pseudorandomness. And this paper is, there's no preprint yet, but I think Sam has given recorded talks. This is with co-authors from Berkeley. They show that pseudorandom codes don't exist unconditionally in the random oracle model. So they seem to be stronger than one-way functions.
So is it okay? Never mind. We can talk about it.
Sure. Yeah, and just to highlight this image watermark a little bit more, all they do is instead of generating an image from random latents, they choose the latents to be random subject to the signs matching the bits of a PRC code word. And this is enough to construct like a very practical image watermark. This is even an actual image watermark using a PRC. So this is worth checking out if you're interested. Okay. So now I'll move on to talking about adaptive robustness, which is the stronger robustness property that I mentioned. So remember I said that extra error tolerance of the PRC translates to robustness of the watermark, but I wasn't very specific about what kind of robustness you were getting, right? Like the PRCs were robust to random bit flips. So this robustness is like to random changes, which might not seem so useful. And this is because of like the formal definition of error correction for a PRC. Here, importantly, the error that the PRC needs to be robust to is this E that's chosen independently of the secret key. And this is a bit unrealistic because in the setting where you're watermarking AI generated content, usually the user can generate as much content as they want, right? So if you like watermark ChatGPT, the user can keep prompting ChatGPT to get more and more content, and then try to break robustness by taking a response and modifying it a little bit. So this like secret key independent error doesn't really capture the scenario where the adversary chooses its modification of the content based on previous watermark content that it's seen. So yeah, here if an attacker is trying to come up with some x prime that's close to some previously seen xi, then the error can actually depend on the secret key, and that it can depend on previous watermark content that it's seen.
Can the adversary get access to the detection?
Not yet, but later I'll consider that scenario. Yeah, so even like this robustness where the adversary gets encoding access had not been achieved by any watermarks before, or by well, yeah. So the analogous property of the pseudorandom code that we want is an adversary can ask for encodings of messages of its choice, and then at the end of the game, it outputs some C star, which is close to some previously seen code word. And the adversary wins as long as the error that it added to the previously seen code word is sufficiently small, and the string that it gives decodes to something different than the message in that whole code word. Any questions? Okay. And so you might be wondering why this kind of robustness is hard to achieve, because the pseudo-random code words are pseudo-random. And so like intuitively, they shouldn't reveal anything about the secret key. And in fact, this was even conjectured in this open paper by Cohen, Huber, and Schoenbach, that pseudorandomness plus this weaker secret key independent robustness together actually implied the stronger adaptive robustness. So yeah, when I first started working on like trying to show adaptive robustness, I was thinking about like a proof along these lines, like showing that this conjecture is true. But it turns out that weirdly, the original pseudorandom code, if you instantiate it with odd size parity checks, it's actually not adaptively robust. And this is for like super weird reasons. It's like the adversary can take the error to be like the complement of a previously seen code word, but now they need to make it low weight, so they just reset a bunch of bits to 0. And if they take this to be the error, like this actually breaks adaptive robustness.
So the conjecture is false.
The conjecture is false, yeah, which was a bit surprising to me.
It's kind of like you have to construct PRC with some weird property to that.
No, so like the existing PRC that we had, if you just happen to take odd size parity checks, oh yeah, I guess I haven't said what the construction is. I will show it, but basically we use a code that has parity checks, and each parity check is on a certain number of bits. And if that number is odd, now it's not adaptively robust. It's not super important, but I guess maybe this is to build some suspense. Okay, but what we show in ideal pseudorandom codes is that actually the same original PRC is adaptively robust to a constant rate of errors less than 1/4 if you use even size parity checks. And I don't have a good explanation for why this is true, other than the particular attack I said required that if you take the complement of something, then all of the parity checks flip if they're odd size. So kind of weird. Yeah. Okay, and so just to talk about this result, I guess first I'll give a quick overview of the actual pseudorandom code construction. So we build this from LPN, and this felt like the right assumption to use because LPN already says that noisy samples from random linear codes are pseudorandom. And so the natural idea is to construct a PRC as follows. To encode 0, you output a random string. To encode 1, you output a noisy random code word from this code defined by A. And this is pseudorandom by LPN, but unfortunately, LPN also says that it's infeasible to distinguish between the 0 case and the 1 case. So you can't efficiently decode. But what we do is we observe that you can sample this code A with a trapdoor that actually lets you decode efficiently. And our trapdoor is going to be in the form of a sparse parity check matrix P. So first we sample a bunch of log n sparse parity checks, and then we sample our generator matrix A subject to those parity checks all being satisfied. And because the parity check matrix is, each row of the parity check matrix is sparse, if you take P times a noisy code word with low weight error, then actually P times the error is going to have significantly lower weight than you would expect from P times a uniformly random string. So just by looking at the weight of P times a string, we can tell whether this is a noisy code word or something independent of the code.
What's going to have a lower weight?
So if the error added to a code word has
P or the A?
Oh, PE is going to have low weight. So if E has low weight, then PE has low weight.
Dimension is
What about A?
So the P is the parity check
P
matrix.
is low weight. Right?
Yeah.
And A is the.
A is the generator matrix. A will show is statistically close to uniform.
What's the dimension for A? It's log squared n by n.
It's n by log squared n.
Oh, you're writing in this stack.
Yeah.
Secret is.
Yeah.
And then what's the error probability?
Constant rate of error.
I'm sorry, but A is the jewel of P, right?
Mhm.
So does A get specific properties, or is it supposed to be almost indistinguishable?
A is statistically close to random if you don't know P. So if you sample P randomly, yeah. But A must satisfy PA is equal to 0.
And so P will be the factor.
Yes, exactly. Yeah. So what we show is that if you sample A in this way, and A is very tall and skinny, in particular it only has log squared n columns, then A is actually statistically close to uniform. And this is important because it lets us invoke LPN, which applies only to random A.
So you can only get like, it's like subexponential security.
Even worse, we only get
Yeah.
quasi-polynomial. Yeah, so just to spell out our construction, we're going to use the same scheme that we couldn't decode efficiently from before. To encode 0, you output a random string. To encode 1, you output a noisy random code word. But now, because we have our trapdoor, you actually can decode efficiently. So to decode, if you're given some string x, all you do is compute the weight of P times x, and you say that the message was 1 if this weight is significantly lower than what you would expect from P times a random string. Okay. And so now to show that this scheme is adaptively robust, we use the following 2 key ideas. The first is we'll show that the adversary doesn't know anything about the parity checks. And then we show that if the adversary knows nothing about the parity checks, then actually finding an error is information theoretically.
Oh,
Computational assumption here.
No. And maybe that'll become.
I'm surprised. I'm lost.
Yeah, so
I don't understand.
the computational assumption is necessary for pseudorandomness, but the adversarial, like the adaptive robustness, holds information theoretic. Yeah.
Read the paper.
Yeah, well, I'll show the argument now and maybe that'll clarify it. So the first thing we observe is that if you don't know the chosen P, if you just see A, it turns out that there are super polynomially many sparse parity checks that are consistent with A. So here, like, you can consider putting all these parity checks in a much larger matrix, P star, that's like so big it doesn't fit on the screen. And now the second thing we can observe is that the adversary only had access to an encoding oracle, and this encoding oracle only needs A in order to answer its queries. So actually, while the adversary is getting its code words, it's learning nothing about P. It might be learning things about P star, but like it's learning no information about the subset of P star that was selected to be in P. So this means that formally we can model P as being chosen randomly from P star after the adversary has already output its code word in the adaptive robustness scheme. So this means that the adversary has to do something harder than just find an error that's bad for P. It needs to find an error that's bad for the whole matrix P star.
Can you give some intuition about observation 1?
I guess there.
I mean, I think more than.
I don't know if that suffices. I mean, I wouldn't have expected many sparse. Like, what are we saying here? We're saying that, like, if you take a vector in the kernel of A,
Just think of like take log n sparse sums of A, the columns of A.
okay.
There are n columns.
So I take
N
log n,
rotation.
I take log n of them and I sum them.
Okay. They should be
Yeah. I mean, every column is already random, so I don't.
how many? And what's the chance that they will be all zero? It's 2 to the minus log squared n.
All zero.
All zero columns.
Oh, okay.
Okay. Right. And how many columns are there? There are n cubes order log n.
That's going to be comparable.
Yeah, comparable, but you can set maybe parameters.
Yeah.
You're saying I should think about it being like, okay. Is that related to how the argument goes, or is it not?
I don't remember off the top of my head. I'm sure it's related.
Okay. No worries.
Okay, so just restating the previous observation, for any error chosen by the adversary, the weight of P times that error is going to be roughly the weight of P star times that error, just because P is chosen to be a random subset of P star. So with high probability, this quantity will be close. And so now what we show is that for any low weight error, its weight is roughly determined by the weight of P star times E. So what this is saying is you can't find E such that P star times E is much lower than what it should be for the weight of and it, like the reason why this gives you adaptive robustness is that the adversary is trying to find an error that's like too low weight for what it causes P star E to be. Makes sense.
What is rough?
Hmm?
What does roughly mean?
Well, I guess if you're thinking about, I think, well, it's kind of a concentration bound, actually, probably the probability that's not like within like, I don't know, the probability that it's not within a constant fraction is pretty low, right? Because if you're thinking about like P is being sampled randomly from P star, then you can just do like a turnout plot.
Yeah, so I don't remember exactly how good the approximation is, but it's good enough that we can say still like the adversary can't find a like low weight is constant times n. They can't find like a constant times n weight e that causes something to decode incorrectly. So like whatever approximation bound it gives us, it lets us set parameters to know that we're adaptively robust to a constant rate of noise.
Write down all the matrices.
Sorry?
This start is that you write down all the.
Yeah, like you write down all the parity checks in one huge matrix.
All the sparse enough parity.
Yes, all of the
Yeah.
log n sparse parity checks. So this is saying if you like had a super polynomial time decoder that just evaluated P star times whatever you're given, then this would have robustness to worst case error. Okay. And so just to recap, what we've shown is that our original pseudorandom code construction has this kind of robustness where the adversary can query the encoding oracle before choosing the error that it introduces to a code word. But you might wonder what happens when the adversary has access to a decoding oracle as well. And that's exactly the question that we ask next. And we formalize this in a new security property, which we call ideal security. And so this property is going to be defined in terms of an ideal functionality. And this ideal functionality, the adversary has query access to an ideal encoder. So it can query a message X, and what the encoder outputs is just a uniformly random string C. In addition to this, the adversary can ask decoding queries on any string C prime of its choice. And what the decoder does is it checks if C prime is delta close to any previously output encoding answer. And if so, it outputs the corresponding message. If not, it just outputs spot. And this ideal functionality captures both adaptive robustness. Here, like a PRC wouldn't satisfy this ideal functionality if the adversary could find something that was delta close, but did not decode to the same message as before. And it also satisfies pseudorandomness because the encoder is returning uniformly random string C. And we say that a PRC is delta ideal if it's indistinguishable from the delta ideal functionality. Okay, any questions about this definition?
What does the decoder?
The decoder checks if the given string is delta close to any previously output code word. If so, it outputs the message that was used to create it.
Any perfectly correct PRC would give you this, right?
Perfectly correct.
The problem would be that you might decode when you're further from delta than the adversary. Kind of like
Yeah. So in order to be a PRC, it must be guaranteed that like you tolerate some rate of errors, right? But it's possible that you accidentally tolerate an even larger rate of errors. And so here the ideal decoder only returns the message if what it's given is
But delta is permissible, right? This
Yeah.
delta is permissible.
what does permissible mean?
Like, so
You're saying that if it's further than delta, then it should still.
no, you guaranteed that the adversary.
But you don't care what happens when you're further than delta.
Yeah.
No, you do care actually. I mean the reason. Well,
No, I mean the queries that you're asking are always guaranteed to be within delta radius of what was issued earlier.
No.
No, the adversary can send whatever it wants.
Yeah,
This is the response. It's xi if it's closed. So this is giving you. I mean, I guess it's not saying that if it's further than delta, it'll just be like blocked or something, right?
It can be human generated text also, right? Like that's.
I'm looking at the definition. I think
wait,
there
so
is-
the definition, the adversary can carry any C prime it wants?
as long as it's close to.
No, any C prime
Yeah,
it
but
wants.
that's something easy to implement, right? You can check whether it was issued previously.
Well, but you don't want to remember all like
Ah.
Boolean code words locally.
Yeah. So the ideal
So the
functionality,
real world, you're not monitoring.
I mean, it might not be feasible.
exactly. In the real world, the real decoder must somehow figure out if it's delta close to any previously output code word. Which,
If you are remembering everything that is spit out, then there is no reason to do all of this and
yeah.
store everything.
Yeah, and it turns out that this like sharp decoding, like not decoding beyond the error tolerance, is actually important in getting adaptive robustness to hold even with the decoder. Because what this says is you can simulate the decoder without using the secret key, just by looking at all of the previously output code words and checking if any of them are close. So yeah, this property is actually useful to get our transformations to work. Oh yeah, and this is exactly what I was going to talk about next, which is the problem that if your PRC is accidentally too robust, then it's actually possible that this extra robustness could leak information about the secret key. Like you could imagine an attack where you take a code word and query it to the decoder and keep adding one more noisy coordinate and then see when the decoder stops decoding correctly. And then you must know that when that happens, whatever bit you changed last is relevant. And depending on your scheme, like this could leak information about the secret key. And the way that we solve this is we do something that we call like sharpening the decoder. And the idea is that we're going to engineer the decoder to return, in addition to the message, also a random seed that was used in encoding. And now, like if you have this random seed, then you can rerun the encoding algorithm and take the random seed, apply a PRF to this, and use that as the randomness in the encoder. So this lets you get back the original code word, and now you can just check the distance between them. And if it's less than the delta threshold, you return the actual message. Otherwise, you say invalid. But this is just like a high-level description of what we do. We actually need like an authentication component as well. This is in the paper. And you can think of it as like a version of the Fujisaki-Okamoto transform.
Which gives like CCA from security from CPA security. What is the difference?
Yeah, I think that's why they used it. We stumbled upon the same transformation, but motivated differently.
I see.
And one nice thing that this gets us is now it easily lets us go from adaptive robustness without the decoder to adaptive robustness with the decoder, because the decoder can be simulated without the secret key. Okay, and so I've just talked about a small part of what's in the actual paper. In the actual paper, we have many transformations. So we start with the original pseudorandom code construction, and we first construct what's called a 0-bit adaptively robust pseudorandom code. By 0-bit, I just mean that you can't encode a message. All the decoder can do is distinguish noisy code words from independent strings. It actually takes a bit more work to go from that to an adaptively robust PRC where you can encode messages. And in fact, both of these steps from like original PRC to 0-bit and 0-bit to multi-bit, the proofs of adaptive robustness are all very white box in the underlying scheme. So it was a bit surprising to me that we couldn't get a generic proof even from 0-bit adaptive robustness to multi-bit adaptive robustness. This is something I'd like to see, but I don't know how to do it.
From single bit to multi-bit adaptive?
From 0-bit to single bit. So single bit to multi-bit, you can do generically. So here we only even listed single bit because we think of this as equivalent to multi-bit. But 0-bit to single bit is like very white box.
What is 0-bit again?
0-bit is where you can't encode a message. You can just distinguish noisy code words from independent strings. Yeah. And then what I talked about today was all in the secret key setting. So in fact, ideal security is defined only in the secret key setting, but we have a kind of analog in the public key setting that we call like CCA secure PRCs. And we consider those in the papers as well. And all of these transformations, once we already have single bit adaptive robustness, are fully generic. So somehow like adaptive robustness is enough to get ideal and CCA security, but getting adaptive robustness seemed to be more involved. Okay, so that is all I had. And if you want to check out the papers, they are both on ePrint and arXiv. Thank you.